Can you guys hear me okay?
Yes, but hang on.
Okay.
The microphone unplugged because somebody unplugged my computer.
That seems to happen like regularly, don't they?
Yeah.
Yeah, that's pretty nice.
There's another teacher in my room.
Oh.
So, yeah. Fun. Come on. There we go. All right, now we're ready.
Great. All right, so I decided, we're doing okay time-wise, getting through the outline, so I thought I would just take your questions today on either the problem set or the practice test or exercises. We're getting ready to take a test tomorrow on Chapter 2. I've graded those quizzes shortly after class. I will put them up on Canvas, so you can just check Canvas. You'll see a PDF of your graded quiz. You'll see your score, and I'll upload my solutions. So we're taking a test tomorrow and turning in the problem set. So I'll turn it over to you all, see what questions you have.
Can you go over 3C on the practice test?
3B?
C.
C, right. Yes. Oh, yeah. Okay. So, let's see. So we want to find the derivative, and the function they give us is 3x divided by 5x minus 2x squared to the 3/4 power. So, how should we approach it? Like, how do we start this one?
Make it power rule friendly and take the first derivative.
We couldn't, you're talking about bringing this up as a negative 3/4 power. I don't know in this instance that makes it any more friendly. It's allowed and you'll get the same correct answer, but notice that there's an x on top. We don't just have a constant. So, in this, we either use the quotient rule in the form that it's in now, or if we want to bring it up, the denominator up to the negative 3/4 power, it'll just be we'll change it to a product rule problem. And, either approach will work, but there's no immediate advantage to doing that. Which way do you want to proceed?
Quotient rule.
Okay. So I'll just pause here for a second and just emphasize, I like the idea of thinking like, oh, can we rewrite this in a way that like makes our work easier, right? Like an ounce of algebra is worth a pound of calculus. But we just have to be kind of vigilant about where we, when we need to use the quotient rule or a product rule. Do we have x's both on the top and the bottom? So using the quotient rule, right, our f function is the numerator, which is 3x, and that gives us an f prime of 3, so I did the easy one. Let's look at the one that's a little bit more involved. The bottom is a power rule, derivative, so g is 5x minus 2x squared to the 3/4 power. Who wants to start us off on getting g prime?
3/4 times 5x minus 2x squared to the negative 1/4
Yep.
times negative 4x.
Yeah, close. Definitely there's a term of negative 4x, but we have to include the 5 as well. So 5 minus 4x. Okay, there's not an immediate opportunity to simplify G prime here, so I guess we could just start by throwing this in the quotient rule. So the quotient rule is the one that goes G times F prime minus F times G prime all over G squared. A common mistake is sometimes people swap, like, reverse the order of these products. So it's the G times F prime that's always first with the quotient rule, and it matters because it'll throw your answer off by a sign. That might be one thing that you choose to include on the note card. Hopefully you've all made one or you're working on it. Let's just plug this stuff in. So G times F prime. So that's 3 times 5x minus 2x squared to the 3/4 minus F times G prime. So 3x times 3/4 and then all over G squared. I think one thing that makes this particular problem challenging is just the algebra now. Right, because this is definitely not simplified. We know that we're kind of just, I guess, almost at the beginning. Like what we found is equal to the derivative, right? But we've got a bunch of work ahead of us to simplify this. So we're just going to be careful with our algebra, and I guess I'll just, to start off, I'll do the easy one first. When I square the 3/4 power in the bottom down here, right, we raise the power to a power, I know I'll just multiply the exponents. So that'll be 5x minus 2x squared to the 3/2 power. And then we want to work on the top. How do we go about simplifying what's going on up top?
Common factor.
Yeah, and what is that common factor we could take out?
5x minus 2x squared.
Yeah, to which power?
Negative 1/4.
Negative 1/4. We always take the least power, right? So whichever one is less than is the least power. We grab that, and so we're going to take that out. 5x minus 2x squared to the negative 1/4 power, and now we open up some parentheses or brackets, and we see what we need. So the first term that we're going to try to get to, that we're going to try to compose here, is this first one, right? The one in the blue box. What do I multiply by this 5x minus 2x squared to the negative 1/4 power to get that product right there? So we took out a negative 1/4 power. We want to get ourselves to the 3/4 power. So we need the 3, and then what else?
5x minus 2x squared.
Mm-hmm. And that's just to the first power, right? Because these exponents differ by 1. Right, 3/4 is precisely 1 more than negative 1/4, so we just take that to the first power. Then we bring down the subtraction that we have, and now we'll work on how do we get to this product. So what factors do we need to pick up there?
3x times 3 over 4. Times 5 minus 4x.
Mm-hmm. Yeah, and we don't need the 5x minus 2x squared at all, right? Because that's the negative 1/4 power is what we have, and that's precisely what we took out. So we're all set there. And this, now conforms with the pattern that we've seen over and over again when we're kind of doing this kind of simplifying with the product or quotient rule. In one of the terms, after we factor that out, in one of the terms we need those parentheses to the first power, and in the other term we don't need it at all. I think maybe what I'll do next is take this and throw it downstairs. So that'll be a positive 1/4 power in the denominator. And we know we'll be able to do some simplifying there because we have the bases are the same and we'll be able to add those exponents. I'll do that in the next step. And we could actually do a little bit more up top. Now, bear with me. You don't have to do this. If you leave the fraction upstairs, that'll work out okay. But we can actually. I'm gonna factor out. There's no more like algebraic factors. Like we can't take anything else, out without that's got an x. But I'm gonna factor out the 3/4. Just to help me end up with not having fractions inside of fractions. It just makes it look nicer, I think. So if we take out the 3/4, then in order to get to, again, let's see, we'll focus on this first term. I obviously need to pick up the 5x minus 2x squared to the first. The question is, what do I multiply by 3/4 to get 3? And that's 4. So we need 4 times 5x minus 2x squared. And then in the next one, we just took out the 3/4, right? This is the only thing we grabbed, so we need to just pick up those other two factors. So minus 3x times 5 minus 4x. Now we'll distribute. We'll expand those products in the top and combine like terms. I'll add those exponents in the bottom to simplify that. And then, let's see, what does that give us? 1/4 plus 3/2 is 1/4 plus 6/4, which is 7/4. So I've got 5x minus 2x squared to the 7/4 power. In the brackets up here, we've got, if I distribute, we've got 20x minus 8x squared, and then minus 15x plus 12x squared. This 3/4 I'm going to write as a factor of 3 on top and a factor of 4 on the bottom. And then we could combine like terms. In the parentheses on top, we have some like terms to combine. So we end up with 4x squared plus 5x. So there's dy dx. There's a lot of algebra to do there, which, depending on your perspective, makes it kind of fun little puzzle to do. Or, maybe it feels more like a hassle, but I always kind of zen out to algebra, so. Are there questions on like how we went about this one before we kind of move on to any other problems? So this is like a particularly challenging, quotient rule problem just because of the algebra involved, I think. The derivative, like applying the quotient rule is not that hard. We just have to organize and make sure that we've got the quotient rule written down correctly, and be careful with our chain rule, when we're doing all this work over here to kind of set up the pieces that we need. The algebra, I think, is definitely the most challenging part. Other questions?
Go for number 7 on the practice test.
Yes, number 7. Oh, yeah, okay. Yes, good. So they give us a displacement function as a function of time. S is in meters and T is in seconds. So we want to find the function that gives the instantaneous velocity. That's part A. So how do we get instantaneous velocity starting from a displacement function? So think of it this way. Maybe I'll re-ask this question. Units of displacement, right? Is S is in meters. And what are the units of velocity?
Meters per second.
Meters per second. So the velocity is a rate of change of displacement. What is a rate of change in calculus? What name do we give it?
Oh. Slope.
Say that again.
Slope.
Well, okay, yep. Slope. If it's slope, it could be slope if the function's linear. It could be slope of a tangent line if it's not linear. In what's like the calculus word that we give this?
Derivative.
It's the derivative. So when they say find the instantaneous velocity of this object, what we want to do is we're going to find the velocity, which is ds dt. And I know it's with respect to time because the units of velocity are per second, right? So it's units of displacement over units of time, so it's ds dt. I guess this is, if we look at the function as they gave it to us up here, what do we need to use? How do we start? How do we have to approach this derivative problem?
Quotient rule.
Yeah. So we'll set up our quotient rule. Our f is on top. That's 2t, which means f prime is 2. Our g is on the bottom, t plus 4, which means g prime is 1. This quotient rule will be definitely less labor intensive than the last one we just finished. So ds dt is g times f prime minus f times g prime all over g squared. So that is g times f prime, 2 times t plus 4 minus f times g prime, 2t times 1 all over t plus 4 squared. Now, we're all pretty good at staying vigilant with our algebra, so, I don't expect to see this a lot, but I would be remiss if I did not remind us all to resist any temptation we might feel to cancel out those t plus 4s, right? T plus 4 is not a factor on top, which means it's not fair game for canceling. But what we can do is just expand the numerator, multiply that out. So we get 2t plus 8 minus 2t And if we combine like terms, then up top we just have 8, the constant 8. So this is our ds dt, or our, velocity function v of t. Oh, I dropped my exponent, t plus 4 squared on the bottom. That's part A. In part B, they say find the velocity at 2 seconds. So we've already done the hard work. In part B, we're just going to evaluate it when t is equal to 2. Six squared is 36, and that reduces. We could cancel out 4, so that's 2 ninths. 2 ninths meters per second. If it's an application problem, so a lot of times people like approximate, do the division, approximate, and that would be about 0.22 meters per second. Either is fine if you like the fraction or the decimal there. Now, the last part asks us to do some analysis. It says, at what values of t does the object come to a stop? So what do we know for sure about this when the object is stopped? Like, we have a displacement function, we have a velocity function. If we're interested in when this thing stops, what do we know for sure about one of those functions? The velocity is 0. Yeah, so we want to set v equal to 0 and solve for t. So that would be 8 over t plus 4 squared equals 0. And, this is a good example of why we always, simplify. I really don't have to do any algebra at all. I could take, a single step and show it more completely, but just looking at this equation, it's never 0, right? A fraction is 0 only when the numerator is. Right? That's the only way a fraction can be equal to 0 is if what's on top is equal to 0. And 8 is never equal to 0, right? It's a constant. So this has no solution, which means the object never stops. If you want to see it algebraically and not just with the explanation or thinking about when a fraction can be 0, you could multiply both sides by the denominator, right? Clear fractions. And if you do that, on the left side that cancels, so we just get 8. Oops. And on the right side, 0 times t plus 4 squared is still 0, and clearly that never happens. Questions?
Could you go over 6?
Yeah. Yeah, this one actually, the type of question that we're going to answer is actually kind of similar to the one we just did, although not in the context of displacement and velocity. And in number 6, they give us the equation of a curve. Y equals x over x squared plus 1. And we want to know at what points does this curve have a horizontal tangent line? So at what points is tangent line horizontal? So here we're definitely talking about slope of a tangent line. Slope of a tangent line is the derivative. If the tangent line is horizontal, what is its slope?
Zero?
Yeah, it's 0, right? Rise over run. If it's horizontal, there's no rise, right? The y doesn't change at all. So if we want to know at what points is the tangent line horizontal, what we want to do is find where dy dx equals 0. So, if we're doing problems like this one and like the one we just finished, I encourage us to stop, before we just dive into doing algebra or taking a derivative. I mean, taking a derivative is probably pretty good. It's a safe bet that that'll be involved somewhere. But stop yourself and think, okay, how is the derivative related to this question they're asking me, right? So we're talking about tangent slopes, so pretty clearly that's a derivative. And then we want to know where dy dx, where that derivative is equal to 0. And it just sort of rephrases it in a calculus language. Now when we find, boy, today is full of the quotient rule, I guess, right? So I got x's on both the top and the bottom, so that means we're using the quotient rule again. Our f function is x, so f prime is 1. Our g function is x squared plus 1, so g prime is 2x. G f prime minus f g prime all over g squared. And we just plug stuff in again, right? So g times f prime is x squared plus 1 times 1 minus f times g prime. So if I multiply these, I just get 2x squared. On the bottom, I've got the square of x squared plus 1. And if we distribute, we have x squared, well, we don't, I guess distributing a 1, that seems silly. If we just combine like terms, x squared plus 1 minus 2x squared is 1 minus x squared. There's our dy dx. So one advantage, we just did a bunch of work to find the derivative, and one advantage of the way we started when we said, okay, how is this a calculus problem? How is this related to, finding the derivative? And we took a few seconds and we rewrote the problem in terms of like just telling us what our goal is now I have a little reminder that what I want to do now is set this function, this derivative that we found, equal to 0. So 1 minus x squared over x squared plus 1 squared equals 0. We have this equation with fractions, but it's a single fraction equal to 0. When is a fraction equal to 0? Yeah, when the numerator is, so this is just 1 minus x squared equals 0. It's a difference, we could factor it as a difference of squares if you like, or you could isolate the x squared and take the square root. Either way, we'll get the same result. We get two values of x, right? X is 1 and x is -1. Here's the other part that it's kind of a detail. They didn't say at what values of x is the tangent line horizontal. They said at what points on the curve. So that means that we're not quite done yet. We've got most of what we want, but we need the y coordinates because they want a point. A point has 2 coordinates. So let's find those y coordinates. And we're finding y coordinates, not y prime coordinates. So I gotta make sure I'm using the original function when I work this out. So that function is x over x squared plus 1. So when y is 1, or sorry, when x is 1, y is 1 over, oh, just 1/2, right? 1 over 1 squared plus 1, so that's a half. And at x equals -1, we get -1 over 2 again. So we get a half and -1/2, and this gives us our points. 1/1/2 and -1, -1/2. Questions on that problem? Okay, other questions? There will be one problem where you're going to be asked to find the derivative using the limit definition. The type of function that you'll have will be limited to a polynomial, so something, and not a very large degree polynomial, but something where at worst you might find it helpful to use Pascal's triangle. There'll be 1 or 2 limits to start off. So one thing I want to just emphasize or point out here is, like on the practice test, the first problem are 2 limits, right? So 1a says limit as x approaches 5. We don't have to do these out unless somebody wants to see them, but I'm writing them out to kind of make to make an observation or give you a bit of warning or advice. The second one is limit as x approaches infinity, x minus 2x cubed over 1 plus x cubed. So sometimes what I see happen on this test, because we spend so much, I mean, this chapter's so much about the derivative, and like just about every problem we're finding a derivative. Just about every problem. Except on these first types of problems, if you're just asked to find the limit, you're finding the limit, right? This is not, you're not going to use the quotient rule on these two. You're just going to, in the first one, right, you're going to do some algebra up top to hopefully be able to cancel out the x minus 5 so that you can actually let x approach 5. In the bottom one, you're going to do some algebra so that, when you let x approach infinity, it just makes all the terms with an x in it like kind of shrink to 0. But you're not taking the derivative on these, right? It's just an actual limit they're giving you, and they want you to find a limit. Are there more questions on either the practice test or the problem set?
How many questions do you have tomorrow?
Say that again.
How many questions are on the test tomorrow?
Question 5?
How many questions are on the test?
Oh, how many questions are on the test? That's a good question. I don't know, probably, I don't remember the exact number, but I want to say 6-ish, give or take.
Thank you.
Mm-hmm. Are there any other questions?
Could we go over number 1A?
Yeah. This limit right here. One A on the practice test or the problem set?
Practice test.
Okay. So it's the limit as x approaches 5. I'm just rewriting it down here where I have more room. So when we're evaluating a limit, I mean, usually the first thing I do is I just say, oh, what happens if I let x be 5, right? Like, just see if I can plug it in right away. And we run into a problem because we get 0. It makes us divide by 0. And in fact, we get 0 on both the top and the bottom. So we want to do some algebra to see if we can't end up with a factor of x minus 5 on top to cancel. Now, you have two choices. You have a choice. They'll both lead you to the same correct answer. One choice is in the numerator, you could FOIL out the x minus 3 squared. You'll get this quadratic, combine like terms, you'll get a quadratic, and then see if you can unfoil it. The other option is if we happen to recognize that what we have up here is a difference of squares, right? I've got x minus 3 squared is obviously a square, and 4 is 2 squared. So we could rewrite this as, factor it as a difference of squares, x minus 3 minus 2, x minus 3 plus 2, and then we get x minus 5 times x minus 1 over x minus 5. Also, keep in mind, I'm carrying the limb all the way through. We carry that limb through each step until we get to the point where we can let x approach 5, which we're just about there. We cancel out the x minus 5s, and now I can let x approach 5. 5 minus 1 is 4. Other questions? Okay. If there aren't any other questions, then I'll let you use the rest of your class time to either finish up the problem set or, work on that practice test. I will get those quizzes uploaded to Canvas in just a little while, so you could check there in about 20 minutes or so, and you'll see your graded quiz. If you have questions between now and tomorrow morning, feel free to email or text. I will see you all on Wednesday, and we'll keep working through that chapter on applications. Enjoy your day.